I'm starting. Hello everyone, my name is Emre. Today I'm going to present a paper which name is Opportunities at the Frontiers of Spintronics for Biospin Journal Club. This paper is published in Physical Review Applied in the year of 2015 by Axel Hoffman and Sam Beder. Before mentioning to this paper, I want to give simple introduction about the Spintronics. It's most basic, the transmission of the information by utilizing the spins and magnetic movements of electrons is called spintronic. So in this field, logical operations can be performed by the making use of the up or down state of the spins of the electrons. Okay, if we move on the article, this article mainly deals with the phenomena in the field of spintronics. The first of these phenomena is spin orbitronics, which aims to generate spin currents even in non-magnetic materials using various spin-orbit couplings. Secondly, it is spin caloritronics, which allows interaction with couplings to the thermal bath. And the third one, the phenomenon in which spin wave excitations are used instead of spin currents is Magnonics. And finally, it is spin photonics that deals with the interaction of magnetism and light. Okay, let's now take a look at the spin orbitronics and spin Hall effect. At first, it was said that it could only be achieved by passing the load current through a ferromagnetic layer. However, as I have just mentioned it before, it has been understood that spin currents can also be produced from non-magnetic materials with the help of spin orbitronic. One of the key phenomena named is the spin Hall effect in this field. The spin Hall effect is mainly caused by the spin-orbit interaction acting like a magnetic field. As can be easily see in the figure, opposite spins accumulate the lateral surfaces of non-magnetic sample through which an electric current is passed. Due to the spin difference formed in this way, spin current occurs. Okay, if you look at the figure, we see a three-terminal device used to show the magnetization transition with the spin Hall effect. By passing current through the tantalum layer, as you can see, spin accumulation occurs with coffee B, magnesium oxide, coffee B, tunnel junction stack. In this layer, as we mentioned above, there is an orientation depending on the spins. When looking at the spin Hall angle of tantalum, it can be understood that spin current and the change current occurs. By making various adjustments to the dimensions, this phenomena can be used in various applications. Okay, another effect on the rise is Dzyaloshinski-Moriya interactions. As spin Hall effects are generally related to heavy metals, this effect can basically be described as an indirect and asymmetric exchange interaction. Based on the equality of DM interactions and necessity of the minimizing energy, DIG should be perpendicular and opposite direction to the cross product of the CI and CG. So this interaction is the very important role of the rotation form for spin configuration. As we can see in the figure A, we can see chiral Neel magnetic field balls with platinum, cobalt, magnesium oxide composition. Here, arrows which represent HSL indicate spin domains that cause both types of domain walls. As you can see, up to down and down to up, to move in the same direction against the electron flow direction. And these arrows are due to the transfer torque resulting from the spin Hall effect as a result of this situation. Up to down and down to up field walls are affected by magnetic fields in different ways, such as up to down is, we can see, parallel to layer, and down to up is anti-parallel to magnetization. Right, then this leads directly to my next point, which is skyrmions. With the contribution of DM interactions, complex spin textures, which known as skyrmion, emerge that are discovered in longer and thinner films and materials. Also, these structures have basic features. The first of these features is topologically protected. They are. And this expression basically means that if you change the direction of the spins to its opposite direction, you will achieve the opposite topological charge for spins. Secondly, they have chiral spin textures. Basically, chiral meaning is asymmetric in such a way that the structure and its mirror image are not superimposable, such as our left and right hand. So if we take a random radius direction one side to other side of the skyrmion, these cannot be superimposed too. To better understand these and other key features, we can look at our figure below. Firstly, as we can see in the part C, we have a bulk-like DM interactions. For the bulk-like DM interactions, the spins are rotating parallel to plane and DM interaction perpendicular to plane. So, as in this situation, vortex-like resembling, we can say, the block domain wall skyrmion structure is created. Secondly, as we can see in the part B, we have a interfacial DMI at the interface of the non-magnetic material and a magnetic layer. DM interaction pointing along the out of the lateral surface direction, and we can see the spins are rotating perpendicular to interface and forming these Neel type skyrmion. So in this situation, it creates a hedgehog-like, so Neel domain wall skyrmion as in B. Finally, as we can see in this part, magnetic skyrmions are so promising and effective things for data storage. Well then, in addition to the spin-hole effect based on the charge current that we have just mentioned, the spin caloritronics research area has also emerged, which examines the interaction of the heat gradient with the spin and charge degrees of freedom. The key phenomena in this area is the spin-Seebeck effect. Before moving on the spin-Seebeck effect, I would like to briefly talk about the Seebeck effect so that its relations can be understood more clearly. Temperature differences between metals with different Seebeck in system produced voltage proportional to their differences. So if you move on the spin-Seebeck effect, these Seebeck coefficients we have mentioned are also different from each other in spin up and spin down electrons. Thus, the temperature difference triggers the voltage difference, the differentiation, and this voltage can be detected with the inverse spin-hole effect. Now we can examine the experimental setup showing the spin-Seebeck effect. There is a film of permalloy and the temperature gradient we can see in this part. So this part of the film is higher temperature than the other side of the film. Also, platinum strips here, and they measure the voltage as I will indicate the later slide. So the result of the fact that the spin current is produced by the spin accumulation in the layer of the in the bottom of the layer. So these effects formed from the thermal gradient. So if we want to examine the change of voltage in more detail depending on the point where the measurement is made, we can look at this graph. Actually, the bottom layer of this graph, which is YIG, and the bottom layer of these figures, which is permalloy, are not same, but the basic principles of effect on voltage with spin-Seebeck effect will be the same. So in this system, in figure A, it contains a yttrium iron garnet, a ferromagnetic insulator, and platinum, a material with a large spin-Hall effect. As a result of the thermal gradient created by the independent heating elements, a voltage perpendicular to the magnetization direction is detected. As seen in the figures B and C, the voltage may be of opposite sign depending on the measurement location. For example, at a point where the temperature is low, in the first figure, the voltage taken over the platinum gives a negative result. However, we can see that the voltage increases linearly with the thermal gradient. On the other hand, if you make the measurement from the high temperature side, we can see that the voltage increases linearly on the positive axis this time. Finally, if we remove the platinum layer and try to measure only on the bottom layer, we get the gray curve we see in the graph. This curve is basically proof that this effect is the spin-Seebeck effect. We anticipate that the spin-Seebeck effect will transform basic research on spin currents and lead to dramatic advances in some spintronic devices. Sorry. Okay, we can continue with the next topic, which is Magnonics. Spin waves are fundamental particle excitations are magnetically ordered systems and are called magnons. To be more precise, we know that the quasi-particle of light is photon, and similarly, the quasi-particle of spin wave is magnons. So Magnonics' main aim is investigate the behavior of spin waves and nanostructure elements. Magnons can be used to carry information, just like electrons. Magnons has several advantages, such as scalability to the nanoscale, energy scale, energy efficiency, room temperature stability, and efficient nonlinear effects. However, working with Magnonics also has several challenges. These are medium carrying magnons and difficult to combine with other materials. The feature being scaled below approximately 100 nanometer and limited spin wave propagation length. For these reasons, electrons are still widely used instead of magnons. Many researchers currently working in this field are using a material called yttrium iron garnets, which called YIG. This material, which you can see in the Magnonic transistor here, has several advantages, such as being an insulator, having low spin damping, and the largest spin wave lifetime. For these reasons, YIG is preferred, but its combination with other materials can be problematic. So nonlinearity is one of the most important Magnons features for the wave-based devices. Based on this feature, the idea has emerged that a magnon creates a magnetic current by controlling another magnon. And we can say that this system can be used to control a whole computer, reducing the difficulties of magnons and disseminating them in this field will make a great contribution to today's technological requirements for information technologies. Okay, now let's talk about the Magnonics Multiplexer. Actually, this figure you can see belongs to a Magnonics demultiplexer. However, these two structures are the same in principle. They are only opposite to each other. As can be seen from the figure, we can think of these structures as magnetic field control, phase correction, and frequency distributor at its most basic. Looking at the figure, we see a simple demultiplexer with one input and two outputs. These paths connected to the design region. Also, an external magnetic field is applied perpendicular to the device. Thus, we get spin wave with two different frequencies. One of them is 2.6 gigahertz and the other one is 2.8 gigahertz. Okay, now it will be much more useful to look at the Brilliant light scattering, which call this BLS images for the behavior of these spin waves. Spin waves can be locally controlled by the application of magnetic fields. These demonstrate by the spin wave multiplexer. It is seen that there are spin waves with a frequency of 2.75 gigahertz in A and B part. Since the frequency of the return waves perpendicular or parallel to magnetization creates an anisotropy, it causes the return waves to be limited to paths that can be selected by controlling the direction of the charge flow. As you can see in the part A, destructive interference is observed in the right path, while constructive interference is observed in the left path. In short, local magnetic fields enable the spin waves to be selectively steered on the left or right side. On the other hand, transverse magnetization state causes a strong non-uniform internal field distribution. In figure C, since the load current are replaced by a uniform external magnetic field, the return waves end at the, we can see, connection point. I mentioned in this section, we can say that the field of Magnonics is also extremely important for future information transfer devices. Well, now let's turn the last Spintronics subfield in this article, spin photonics. The main thing in this subfield is manipulation of the magnetic order on the ultrafast timescale. In addition, while doing this, it provides a controlled frame. Therefore, we can say that ultrafast magnetism is also called laser controlled magnetism. And the heat that will occur should be minimized in this part. For this reason, the basis of the studies in this field is to convert the magnetism created when we send the laser into a spin current that can be used in the femtosecond time intervals and use it in spintronic devices. After giving a brief basic information, we can examine some more experimental studies. We can say in this figure, as you can see, laser pulse come and heat up the thin ferromagnetic film. Thereby, we induce thermal disorder and dissipation of the angular momentum. This process is just heating, but the fact that it happens very quickly makes it special. Because this ultrafast laser heating is also produce carriers which are mobile, in thereby you can induce transport the spin current. Okay, let's look at the angular momentum and spin situation in more detail. In figure A, we have a non-collinear magnetic layer before pulsed laser excitation. Then, as we can see in option B, angular momentum transfer takes place between the layers after the laser pulse. And then we can say precession is observed when the excited electrons change the existing orientation with the STT, spin transfer torque. And we can say that we can switch the magnetization in a ferromagnetic alloy using a single femtosecond laser pulse. So, as I said before, because of this ultrafast laser produce carriers which are mobile, in thereby you can induce transport as a spin current. Okay, now let's look at the next slide, which shows the graph of X-ray magnetic circular decoration of GD and F. We see that the sample with an ultrafast laser pulse, the magnetization for GD and F start much higher. The main reasons for this situation is the different spin relation times of the electrons in the f orbitals, so rare earth metals, and d orbitals, so transition metals. Thus, an f electron spin system can take longer to equilibrate after laser pulse excitation. Also, at high spin temperatures, the magnetization of the transition metal dominates. In short, iron demagnetizes faster than the gadolinium. When the iron reaches zero, a temporary ferromagnetic state is formed. But the system is not stable in the state because it seeks an antiferromagnetic state. For this reason, magnolium transfers its angular momentum to the iron, causing the iron to become magnetized again, and both elements began to magnetize in the opposite direction to their previous laser excitation. Thus, the total net magnetization between palladium and iron is preserved, not even those directions are changed. In conclusion, there are many opportunities for ultrafast spintronic based and optically induced spin currents, such as the possibility of increasing the response speed of bits by 1000 times. Okay, as a final point, I would like to say that we examined the studies in subfields of spintronics, such as spin orbitronics, spin caloritronics, Magnonics, and spin-photonics, and take a look at the opportunities here. While each of these areas reaching not only theoretical physics, but also applied and research fields. Also, spintronics can help with the miniaturizing the thermal issues in today's silicones technology. For these reasons, we can say that smaller and faster information processing and data storage devices will be available in the future, thanks to the subfields and their studies in spintronics. And these are my additional sources. Thank you for attention and time.